Hello everyone, I hope you're doing well. In this video, we'll have a detailed look on the variational method. We'll see what is the applicability of this method, like where to use it. If you're given with some problem in exam, then how you will determine that what method to use. Okay, whether I can use the variational method here to solve that problem or not, whether the variational method would be helpful for me to solve that kind of situation or not. So you should know what is the applicability of any method that you have learned. First of all, let me tell you people that the variational method is a method to find out the wave functions and eigenenergies of the system under study. Okay, now which systems are best suited for this method? This is something that we have to understand, and we'll understand it obviously in the introduction part. So let me first clarify the structure of this video. First of all, we'll have an introduction to this method where we'll discuss all of the important points regarding the variational method that we should know. And after these initial points and understanding that method, we'll see the mathematical discussion of this method that is really important, and which will actually describe this method. And yeah, this video is very detailed video because we will know each and every point regarding this method, and the mathematical description is really important to understand how to use that method. And after this video, I'll upload videos on the solutions of the problems which were done using this method. Okay, so stay tuned, and I'll make the chapters so that you can jump to your desired part. If you already know what is the variational method and where we use it, what is its range of applicability, where it's best suited, which states are bestly bestly determined by this method. So if you already know all of that stuff, then you can directly jump into the mathematical part. Okay, so let's quickly get started. First of all, let me tell you that the variational method is used to determine the wave functions and eigenenergies of the system under study. Okay, these systems includes the hydrogen atom, the system of harmonic oscillator in quantum mechanics, and the quantum mechanical treatment of particle in a box, finding out their wave functions and eigenenergies. So we use this method to determine the wave functions. Okay, for example, the wave function of a hydrogen atom and the eigenenergies associated with it. For example, the ground state, the first excited state, the second excited state, all of these are determined using this method. There are various methods to find out the wave functions and eigenenergies of these systems. For example, the first method that we were introduced to was using or solving Schrodinger's equation to find out the eigenfunctions and eigenenergies. This is the first most method that we were introduced to, and there are tons of different methods that we can use to determine the wave functions of the system and their energies. And all of those systems gives different, their method obviously is different, and the quality of output they give may differ from one method to another method. Okay, it depends on various factors. For example, in variational method, we will see the guess we can make about the wave function, the best answer we will get. Okay, so here the quality is sensitive to your educated guess. Okay, if your guess is really good, then you can use this method very well to determine the wave functions and eigenenergies. If your guess is bad, then that method is very bad for you to use. You should use other methods. But if you are a student, and if you are a student and you have to use this method to solve some of the systems in exam, then it's better for you to practice as much as possible, like solving different problems using this method, so that your guess becomes very good. Okay, you will see what is the role of guess in later part of the video, and also in examples that I'll post after this video. Okay, I highly recommend you people to practice examples or problems, because they deepen your concepts and they make your learning process way easier. Okay, so like all other methods, variational method is also one of the method that is used to determine the wave functions. Okay, this method is used, the variational method is used to determine the wave functions, or another word is eigenfunction, or another word is eigenstate. You should be familiar with all of these equivalent words for the wave function. Okay, because in different books different wordings are used to symbolize or call certain things, so you should be familiar with, like, they are similar things. Okay, wave function, eigenfunction, eigenstate, and eigenenergies of the systems in quantum mechanics. In quantum mechanics, like system of hydrogen atom, you should give example of systems, harmonic oscillator. These are very common systems. Oh, harmonic oscillator, it's harmonic oscillator, and particle in a box, and many others, etc. Okay, now we already know about the perturbation theory. It's one of the method to find out the wave functions of the perturbed systems whose Hamiltonian can be compared to some related Hamiltonian. Okay, some related Hamiltonian whose solutions are already known. Okay, I hope you are understanding what I'm trying to say. It's like we know that for example, if you have a case like a Stark effect, case of Stark effect. Stark effect is like electric field. In the presence of electric field on hydrogen atom, what happens to the eigenenergies, what happens to its wave function. That is something that we wanna study. That is a system. Okay, that Stark effect is depicting a system whose solutions needs to be determined. What we'll do, we'll use perturbation theory. But what happens when we use perturbation theory? What we did is, now this is a different system, like let's say it has a Hamiltonian H prime. What we do in perturbation theory is that we relate that system's Hamiltonian, which is different, okay, to some other related Hamiltonian, like Hamiltonian of hydrogen atom, unperturbed hydrogen atom. Okay, and we say that it is just a linear combination of that unperturbed hydrogen atoms Hamiltonian and some small perturbation, which is electric field, energy due to electric field. Okay, so what we do is that we compare the new Hamiltonian whose wave functions and eigenenergies are not known to some another Hamiltonian, related Hamiltonian, that is really close to this one, whose solutions are already known. Like we already know the solutions of hydrogen atom and its eigenenergies. Okay, and it can only happen if we know and if we have some related Hamiltonian. But in perturbation theory fails if we do not have any related Hamiltonian whose solutions are already known. Okay, this is the limitation of perturbation theory. So let's say we never heard of hydrogen atom and we are never not known about its solutions. So perturbation theory will not help us to determine the solutions of hydrogen atom itself at first place. Okay, because for hydrogen atom there is no related Hamiltonian whose solutions are known. Okay, we have to start from the 0 point with blank information, like no information about hydrogen atom. We have to start from 0. Okay, so the variational method is a method to start from 0. Okay, for the basic systems. Perturbation theory has that. I was just conveying you uh, the comparison between the perturbation theory, like where the perturbation theory can be used and where the variational method could be used. So this is the limitation to perturbation theory, that it can be only applied to find out the solutions of those Hamiltonians which can be compared to some related Hamiltonians of known solutions. Okay, and now I was gonna write such a statement, and I just wanted you all to understand that statement, and that statement makes sense when you know about perturbation theory. Okay, so let me write that statement now. I hope you caught it, and I hope you will get the statement as well when I write it. Now, in quantum mechanics, or you can start the line from in quantum mechanics, we are interested in finding out the eigenstates or eigenfunctions represented by psi or phi or what else that you prefer, and eigenenergies of the system, eigenenergies that we represent by E of the systems of the system. There are various methods to find eigenfunctions and eigenenergies of the systems. Eigenenergies of the systems, including solving, we can write it as number 1, solving a Schrödinger's equation, given by H operator, Hamiltonian operator applied on psi, that gives E into psi. Okay, where psi is the eigenfunction and E is the energy or eigenenergy, you can say eigenenergy, and H is Hamiltonian of the system under study. The second method is perturbation theory. Perturbative treatment, you can say perturbative treatment, where the solutions to a system is determined by comparing that system's Hamiltonian to some related Hamiltonian whose solutions, eigenfunctions and eigenenergies in energies or already known. It cannot be used to systems whose comparison doesn't exist. Okay, and the variational method you can write as 3, or you can write it in paragraphs. It's better to write in paragraphs because these numbers looks childish to me. And the variational method, just like Schrodinger's equation, but unlike perturbative treatment, this is used, like I'm linking this variational method with this, is the variational method is used to determine eigenstates and eigenenergies of the basic systems whose Hamiltonian is known, but its eigenstates and eigenenergies are not known, and that's why we are finding it. And there is no other related Hamiltonian to our system which is under study. So no comparison exists. Okay, for example, there is no Hamiltonian related to hydrogen atom which can be utilized in perturbation theory if you are completely blank, and the variational method is used to fill that blank. Okay, to know about those basic systems whose previous knowledge is not there. So yeah, I hope you got it. So if we are to use perturbation theory for determining the wave functions and eigenenergies of hydrogen atom, then it's not possible because hydrogen atom is the basic system and there is no related Hamiltonian that exists that is very close to hydrogen atom and whose eigenfunctions and eigenenergies are already known. Okay, so that's the limitation of perturbation theory that we are talking about, and I'm telling you these things because these things are really common when you are studying and comparing the variational and the perturbation methods, because they are the methods that you will be probably studying in your quantum mechanics class. So you should be known about these phrases and these comparisons. Okay, that's really necessary. If you are thinking that I'm unnecessarily making the things tough, okay, that's not the point. I just want to make you familiar with these phrases and how they are, making sense. And if these phrases starts to make sense in your mind, then you can use them in your writing while writing down the exam, and it will improve the quality of your writing. Okay, so yes, here the things I'm writing here, okay, these are for the neat notes. Okay, all other things that I'm saying are just for making you people understand. Okay, this is the structure that you have to follow while making notes about the variational method. First of all, what we did is to introduce the variational method, that what it tells us. It gives us the wave functions and eigenenergies. Then we talked about, like, we have other methods in quantum mechanics as well. So we talked about those methods. Schrodinger's equation becomes very difficult okay, to solve. You will see the variational method is way easier. All right, it's really easy method to determine the wave functions and eigenenergies. It's really easy. So we should know about different methods, and that's a task. We are always searching for alternative methods that can shorten down the process of solutions. Okay, so we are always looking for different alternatives, and that's a good thing. We should know about it. So first we talked about the Schrodinger's equation. We wrote it and we talked about the things in it. Then we talk about the perturbative treatment, the perturbation theory. We elaborated the fact that what is the limitation of that theory, and it can be used for, it's a easy, it's a very easy method, but why we can't use it for the basic systems, we talk about it. And we said that since no previous knowledge exists for it's never possible for us to determine the wave functions of hydrogen atom using perturbation treatment. Okay, here we talked about the limitation of that perturbation theory, that why it can't be used to determine the wave functions of those basic systems, and where it is applicable, and why we are not using it, since it's a really easy method. Perturbation theory is really easy to use, and it's really easy. And then we talked about the variational method, and we saw here that the variational method can be used to determine the eigenstates and eigenenergies of those basic systems whose related Hamiltonian doesn't exist. And it's quite an easy method, but there are some limitations to this method as well. You will see later on that in this method what we have to do is to find out each and everything separately. Okay, for example, if you want to find out, this is something that I'm writing in rough space. Okay, now the mathematical discussion has to be started. So before that, I just want to mention the cons of this method, and that's okay, it's not that tough. But what happens here is that first of all you have to find out the ground wave function separately. Okay, if you know the ground wave function, then you can find out the ground state energy. Okay, and if you know both of these quantities, then you can find out the first excited state and the first excited state's energy. Okay, the wave function energy. If you know psi1, then you can determine psi2 and hence E2. Okay, then it's like if you want to determine psi2, then you should know psi1 and psi0 as well. Okay, if you don't know about these two, then you can't find out psi2. It's like a chain. Okay, and that's something that makes it lengthy, and that is the reason it is only useful for the lower states. Okay, as I told you that in order to know psi2, you should know psi1 and psi0. So what you have to do is to determine psi0 and psi1 first, then you can determine psi2. And what if you want to find out the fifth excited state, for example, then what you have to do is to determine psi4, psi3, psi2, psi1 and psi0, all of these to determine psi5. It's a hectic process, quite a lengthy process. So that is how we can say that this method is not suitable for higher excited states. It becomes complex and complicated, but it's good for the lower states. You'll see I'll explain in the problem solutions that I'll do using the variational method. Okay, you will see that it's quite an easy method to determine the lower states, but it becomes quite a hectic process when you move towards a higher state. So we can here mention that this variational method is suitable for variational method is suitable for lower states, especially the ground state, because it's the first one with the least steps, especially the ground state. That's how we can say it. it becomes quite complex and cumbersome to determine the energy levels of excited states. Though we can use this method to determine the energy levels and wave functions of higher excited states, but the method becomes unnecessarily complex and lengthy. There is no need to do that when you have alternative methods to determine the excited states, energy level, and wave functions. You can use this method up to the point where it is easy to use and not hectic at all. That is for the ground states and the very initial excited states, like the first excited state, second excited state, and it's quite sensitive to the case under study. For example, some of the cases have very simple Hamiltonian and their integrals are simple as well, so the integration process is not that much hectic and we can easily go up to very higher number of excited states. We can reach up to them without getting bored or thinking it as a burden. So it is really a case sensitive thing, but generally we can say in theory that variational method is really easy for the ground states and lower excited states, while it's not ideal method to find the energy levels and wave functions of the higher excited states. That is something that we wanted to say for so long time. So I hope you got it, the main highlights of the variational method, the theory that you can use. Now let's go deeper into this method, that what the method is and how we can represent the whole method by a single equation. There is a single equation that represents the whole of this method, that holds the crux of this method. So let's move towards the mathematical stuff now. Then after some initial equations and representations, we'll move into the steps that we follow to find the energy levels and wave functions of the system under study. And after doing these things in this video, the next video will accompany an example problem. Now let's see how we can in the context of the variational method, one doesn't need to solve the eigenvalue equation. Rather uses a variational scheme to find approximate eigenenergies and eigenfunctions from variational equation. Which is given by, now let's see what is the variational equation, which holds all of the necessary information about the variational method itself. Okay, so let's see what it is. It's this partial sign. This is the partial sign that shows variation. Okay, variation in energy, which is corresponding to a psi state. Okay, because for every state in a quantum system there is associated energy, so they are interconnected to each other. Energy for a state psi and their differential or variation, you can say their variation will be equals to 0. This is the variation equation. Okay, and this is how we can determine the energy levels and the wave functions. Ultimately, what we'll do is to first find out the this is expectation energy. Expectation energy is, in other words, eigen energies. So we'll write the expression for expectation energy, okay, and then we'll find out its variation with respect to whatever the variable is. Then we'll put it equal to 0. We'll solve it, and after solving we'll get some values for the constants that we assumed at first place, and after inserting those constants into that initial expectation energy expression, we'll get the value for the expectation energy. Okay, the whole method will be cleared in a while when we'll be seeing the detailed steps to follow, the method that we have to follow while solving the problems. Okay, now we are just being introduced to some of the mathematical notations used in this method. This is the most important equation. This is like the variation in expectation energy corresponding to a psi state is equals to 0. This is the variation equation. Okay, there is no space here. This is it, where what is E? E is the expectation energy for state psi. It's the expectation value of energy in the state psi. We are writing it in ket form, and we know that formula for expectation value of any physical quantity is like, we write them in these angular brackets, and that is equals to psi E, not E, sorry, it's H, because the operator that gives you the energy eigenvalue is H. So here we write H, and again psi divided by, this is the formula to find out the expectation value of energy, whichever quantity you are considering. For example, if you want to find out the expectation value of momentum, you will write P here, and there will be a P operator here. So the quantity and the associated operator that gives that quantity is written here. Rest of all the things remains the same. Because we are interested in eigenvalues of energy, that is why we wrote E here, and the associated operator that gives eigenenergies is Hamiltonian. That is why we wrote H here. There is no, let me write it again so that you may know how to write it. This is the expression. If I elaborate the method here, what we do is we first assume a psi function. We make educated guess about the ground state wave function of the system, and the things that we are not sure about, we introduce some constants and parameters in the psi function that accommodates those unknown things about the wave function that we don't know or have an idea about. So we assume at first place the psi thing. Okay, we assume it, and then we put it right into this equation. Since the system is at least known, as we know the Hamiltonian of the system at least, so we'll put it here. We put the guessed or the trial function, we call it as a trial function in the variational theory. So we put the trial function right into this equation. We solve this equation, and then what we do is to find out its variation, and then we put it equals to 0. So we differentiate it with respect to different parameters, those parameters which you are not sure about. Okay, for example, let's say we are not sure about two of the things about the wave function, so we'll introduce two parameters, that will be alpha 1 and alpha 2, or alpha and beta, maybe whatever notation you are considering. Then what we do is we write this expression considering a trial function for the wave function of ground state, and then we put in here, we find partial derivatives with respect to alpha and with respect to beta separately, and we put them equal to 0. We find out the values of those constants and we put them into the psi function. This gives the value of that psi function, and after doing that, since we now correctly know the psi function, we can put it right into this equation and solve it exactly to get the value of eigenenergy corresponding to ground state, because the psi which was considered was for the ground state. That is why the energy that we'll get from this function will be for the ground state, and the higher energies could be calculated by using the orthogonality condition, that all of the wave functions, let's say the ground state wave function that we calculated at first was psi naught, then psi 1 needs to be determined. So we'll use this equation, this scalar product, to find out psi 1 since we know psi naught. Okay, and this product is equals to 0. This is the thing that we'll use, and this is the condition known as the orthogonality of wave functions, that is a necessary condition for well behaved wave functions. And we'll see the steps, but here I just thought to clarify to some extent, because most of the students have so many questions in their mind that what is the method. So that is how I call this equation, this variational equation, as the crux of this method. It holds the crux of the method. We first define a trial function for psi, then we put it into the expectation value expression, which is this equation number 1. Okay, this is really important equation. Then what we do is to differentiate this equation with respect to those parameters those unknown parameters that we introduced in this trial function psi. And after doing that, we find out the values of those constants, we put them right into the psi, and we get the psi function. And after getting the psi function, we solve this equation exactly to get the value of energy. This is a really easy method. You'll see when we'll solve the problems. I hope you are getting what I'm saying. Let's continue with it. Here the trial function couldn't be any function. You have to make a best possible guess about psi. If psi is really nearer to the exact eigenstate of the system, then it will give you the exact eigenenergy of the system. So it means what we can say here, that E would be equals to the exact eigenenergy if psi is nearly the exact eigenstate. Okay, as I told you people, what we are starting with is a trial function, and it means that trial function is a guessed function. It's a guesswork. It's your guesswork. Some of you make a good guess about it and some of you make a bad guess about it. To every one of you who have guessed the different psi function will reach the same outcome? No, it depends. It depends upon that how good and how satisfactory guess you have make. It means that the result that you will get is not necessarily be equal to the exact eigenstate, which means there could be a error in the result that you have got for your system. Practically it happens because we are making some guesses and there's not a possibility that we all guess a perfect trial function. So what I am trying to say here, that it's an approximation method. Okay, it doesn't gives you the exact energies for sure or with 100% probability. There is a probability that you may get some value that is slightly different from the original value, and there could be an error, and hence this is a approximation method. And there is a possibility that the E that you have got is maybe greater or lesser than the E you are seeking for, or the original E. So it means that E is not exactly what you are seeking. There could be an error, there could be a difference. So let's dig deeper into it to see some of the other information that we can get from this equation. Now I'm going to write some of the statements which will be justified later on as we proceed. Okay, they are because I'm justifying and explaining to you each and every statement based on what's happening right here. Okay, so trust the process. You will be successful in understanding this method right at the end of this video. And there are multiple statements that we read in book relevant to these articles on variational method, for example, and those statements sometimes are not comprehensible easily to the students. So that is why I'm saying that whatever I'm going to write, they are the statements that I'm going to write, and I'm 70% sure that you will be confused about it, like why and how I can write this, so how they are logically consistent. So these will be justified as we proceed. Okay, so trust me and the process. The minimum value of 1, which is expectation value. What is the minimum value means? This expression can also be alternatively called as the minimization of expectation value of energy. Okay, minimization of energy. This process is also known as minimization of energy. If you know from mathematics, minima occurs where the derivatives of a function are 0. Okay, so that is how we can say this statement alternatively in terms of descriptive words. We can say the variation of energy is equal to 0, or we can say we are minimizing energy. All right, so the minimum value of E means this process, when this process is carried out on E, the values that we get will be the minimum value of E. This is E now, and there could be many E's possibly depending upon the trial function you are considering. So what we are seeking is we are finding out the minimum value of E, and we will see what the minimum value of E gives us. The final value that we take from this method is the minimum value, not any other value but the minimum value. What does that minimum value gives us? And all of the advantages will be uncovered as we proceed. Trust me. The minimum value of E provides an upper limit approximation. It gives you an upper limit approximation for the true energy of the system. Let's say the true energy of the system is E0. Let's say it's the true energy of the system. So the minimum value of E that we get from this variational scheme, this value gives you the upper limit approximation about the true energy of the system, because as I told you people, it's not necessary that the E you get from this method is equal to the true energy. But what else we can say about this result that we have got? We can say that it is the upper limit approximation. What does upper limit approximation means? Upper limit approximation means that, for example, this is the original energy of the system. Okay, low limit approximation means the approximated value that you got is less than the original value. That means the low limit approximation. And if you get a value with upper limit approximation, which means that the energy that you will get for sure will be greater than the original energy. Okay, that is something that you can say for sure about the energy that you will get from this approximation method. Okay, the energy that you have got as a result of this method would be greater than or equal to E0, but it will never be less than E0. That's the thing that you can say for sure about this outcome you'll get from this method. Okay, the energy that you will get will be equal to or greater than E0, but it will never be less than that. This is what upper limit approximation means. So the minimum value of E provides this minimum value that minimizing it gives you the value E, which is the upper limit approximation for the true energy of the system. Okay, the outcome that you will get will be equal to or greater than E naught, but it will never be less than that. And we can prove this statement. Now let's prove it. Let's first write this statement in terms of mathematics, which means that we got E from this process, and we know that E is equals to this thing. I'm writing this again here. It will be greater than or equal to E naught, but will never be less than that. Let's prove it. And you must be asking that when it will be equal to E naught, because we want it to be equal to E naught as we are interested in true energy value. So it will happen when the psi you have chosen, the trial function that you have got or guessed, is the true is the true eigen function of the system. Okay, so it all depends upon the psi you have guessed at first place. If it the best the guess you make, the closer you will get to the original value of energy. Okay, now let's prove this statement. Let's call it as 2. Now we can express psi in terms of linear combination of psi and states. We are very familiar with this representation when we express a wave function in terms of linear combination or superposition of many orthogonal wave functions. Okay, since we are using the cat notation, that is why I'm using cat on every wave function. This is wave function and this is wave function also. So we are expressing the psi in terms of the linear combination of many other psi function, because this is very familiar representation. For example, we have psi, then we can express it as 4 psi 1 plus 5 psi 2 plus 3 psi 3 and so on. Okay, this is a possible representation that is very common in quantum mechanics. Now equation 1 becomes, which was this, in place of, we'll do this thing gradually. Let's put this thing right into this equation, where wherever the psi is, put summation and a and this thing. Okay, so since we are using them here, you are not supposed to use this again right here. Okay, it will be wrong to do this. All right, now what we can do here is to take one summation, this summation side, since it's common from both, we can write it once like that. It's not necessary to write separately for both summations if they are exactly the same summations. The same can be done here. Summation shows a kind of operator, and they cannot be cancelled from below and above. You can't cancel them out. They are not any numbers or thing like that. They are just operators, which means we have to sum them up, and these things never cancel out. Now this is an and this is an, and they are both constants, and constants can come out of the integration. This is actually the integration, so they can come out of the integral. And this one and this an, they both multiply, since they are same, so it becomes an squared, and what we are left with is psi n, and in the denominator the same thing happens, and we are left with psi n this. Since the functions that we have considered here are orthogonal as well as normalized, that is why this will give you answer of 1. Hence we are left with this thing, and psi n h psi n. And now let's solve this thing right here. When a h operator is applied on psi n, since we are actually applying h operator on psi n using the cat bar notation, we'll remove that bar now and it will be simply applied on it. Applying a Hamiltonian operator on a psi function of nth state will give you an energy of psi function of nth state, okay, which means if Hamiltonian is applied on psi n, then it gives you this En times psi n. Okay, this is the simple eigenvalue equation. If h is applied on the ground state, for example, the energy it will give you will be the ground state times the wave function again. Okay, so this is what we will write in place of h psi n. This is something that we will write, En into psi n. We'll write here En into psi n. Let me do it. Here we are proving something, a statement, and this is the fun part. You should be able to do that. To psi n divided by summation a n squared. You can't cancel them out, okay, even that is not possible because it has some extra term right here. If they would be exactly the same thing, nothing else, then they could have been cancelled out, but you can see there are nth terms here, so you cannot exactly cancel them out. And En is a constant quantity. Now you can bring it outside of the this operator. Let's say right here. You can write it here as well, it depends. Now this is an orthogonal function, so and normalized as well, so it will give you one result as we did for the denominator, and this is something that you are left with now. This is the expectation energy. Here En is the energy level of the original system, is the exact energy levels of the original system. E is the expectation value that we are getting from the variational method as to be the expected value of energy for the system under study that we are getting using the variational method. Here En can be greater than or equal to, here En are the eigen energies of the system. That could be the excited state, ground state, or anything. So we know that the ground state is the energy of least value. Then we have excited states of greater energies. Alright, so it means we can write in general that En, which shows that, which is a general representation of eigen energies, would be greater than or equal to E naught. We can write this equation. Alright, yes, we can write this equation because we know that, for example, if we are talking about if we put this one second, so En is greater than E naught. Let's see how this statement is true. If we put n equal to 0, which means E naught is greater than or equal to E naught, it's satisfied, that is justified. Obviously it's equal to it. Now if we put n equals to 1, if we think about the first excited state, so E1 is greater than or equal to E0. That's a true statement. That is, E1 is obviously greater than the ground state energy. The first excited state is obviously greater than the ground state, and obviously E2 will be greater than E0 as well. E3 will be greater than E0 as well. So in general we can say that these are excited states, and starting from E0, so we can write in general that En, the energy levels, the eigen energy levels will be greater than or equal to E0. This is a statement that we can say for sure. And why the energies here, the eigen energies, the reason is that the wave function that we have expanded into, we expanded it into the eigenstates of Hamiltonian, this Hamiltonian. It means that these psi n's are the eigenstates, original eigenstates of Hamiltonian H, and application of Hamiltonian on its eigenstates psi n will obviously give you the eigenenergies of the system, which are the original eigenenergies of the system. And the difference that appears between the original eigenstates and the trial function is because of this thing. Okay, so that's not necessary that they are equal to each other. There is a difference that's originate because of the guesswork, but we have done it to prove a certain thing, that we have expressed the trial function as a linear combination of the original eigenstates. Okay, we have just made a clever assumption that gave us some hints about the outcome that we are gonna get. So this is the thing that we can write. Now let's put this thing here. What happens? Let's see. So let's say this is equation number 3, this is 4. Let's write this thing right here. What happens is En squared, so it's En by an An squared. So this thing will be, what I just did is I multiplied both sides with this thing. The same could be done here since it's a constant, so that doesn't matter if the summation is written on the right side or the left side, because E0 doesn't have n in it, so it can come out of the summation easily, and above and below it will be cancelled out and we are left with E0. So this whole thing will be greater than or equal to E0 as well, right? Let's do it in steps. All right, I hope you got it how I write this. I write it using the equation number 4, the inequality number 4. This is not equation means something which is equal to each other. This is inequality, so I wrote it using the inequality number 4. And since E0 is a constant, it will come out of this thing, summation, and they are exactly equal to each other, so they will cancel out and we are left with this thing. Is greater than or equal to E0. This is the expectation energy that we are getting. Okay, this is what we are getting from the variational method. Okay, and this is something that we aim to get. So it's a possibility that it will be greater than or equal to E0. That's how we can prove it. Okay, this is something that we are getting using the variational scheme, and it's a possibility that it would be it's a possibility that it would be equal to, or it's a possibility that it's greater than E0, but it will never be less than that. That is something that we can say for sure. That's how we can prove the statement that we wrote at first place, that the minimum value of E that we will get, obviously the value of E that we can get is by the minimization of E. Okay, so it means the value that we'll end up getting is the minimum value of E. So the minimum value of E provides an upper limit approximation to the original energy of the system, to the original ground state energy of the system. Now let's write some more of the statements, and all of the things that I have mentioned here, you can add them as your description when you are talking about the variational method. And after this discussion, we'll see what four major steps you have to follow in order to determine the ground state energy of the system using the variational scheme. Okay, and those steps will be uploaded in a separate video. The reason is the video is already very concentrated, or we can say it's very lengthy, and the reason behind its huge length is that it's a one video that is explaining you the whole method. It's a whole method and it requires multiple videos in order to be delivered effectively, and I'm sure that there is no video that explains this method that well as I did, because I didn't get any when I was learning this method, and I learned it my way from multiple books and all that stuff. So I assured that I answered your all questions and clarified all of your confusions. Even if some of your questions are not answered yet, you can ask them in the comment section. Either I'll reply to you with the reason or the answer to that question, or I'll make a video about answering that question if that question's answer requires additional or specific consideration. Okay, so once we know the energy for the ground state, we can determine the approximated wave function, approximated ground state wave function, ground state eigenfunction, you can say in other words. Let's denote it by this symbol, this cat. Okay, once we know, let's write E naught here just to show that it's for the ground state. We can determine the approximated ground state eigenfunction once we know the approximated here as well. Okay, to be specific, because we will get an approximated energy that could be potentially equal to the exact energy, but that's an exception depending upon the trial function, the quality of trial function you have chosen. So once we know the approximated energy for the ground state, we can determine the ground state wave function very easily. And after we know the wave function for the ground state, we can determine the first the eigenstate eigenfunction, sorry, determine the eigenfunction for the first excited state using another trial function for the first excited state, the orthogonality condition, and the variation scheme and the variation equation. And similar process is repeated for higher states as well. For determining the higher states, as well. In principle, this method could be used to determine any excited state to determine or approximate as well. You can use both of these words, excited state, but the method is ideal for the lower excited state. Ideal for the lower excited states. Lower excited states. As the method becomes increasingly complicated for the higher excited states. How we can say this, why the method becomes increasingly complicated? This statement has been justified in the video, but it will be justified even more in next part of this video, where we'll discuss the 4 major steps to follow while finding out the ground state energies for the system. These are very 4 easy steps, not so easy, but comparatively but in comparison to other methods, it's really easy. Those 4 easy steps has to be followed, and these are actually the basic steps, and they are replicated again and again to determine the other higher states. This is the general as well as detailed description of the variational method. In next video, we'll be seeing the 4 steps, the 4 major steps, the basic steps to follow in order to find out the ground state energy of the system using variational method. And that video will in detail covers the actual method, the actual practical method, the steps that we follow in problem solving. So if you are here to understand the variational method in order to solve the problems, then do watch that video. It will be very helpful for you people. And in that video, we'll see how to find out the higher energy states as well, because in problems we are asked to find out the first excited state, second excited state at least, or we are asked to write the formulas to find those energy states if we are not asked to solve them at least. Hence, stay tuned. I'll link that video right in the description box or in comment section. If you have any queries, you can ask me, and subscribe and share to other people, because if that video helped you, then it can help others as well. We'll see you in next video. By the way, the links to the problem that were solved using the variational method, or the problems related to variational methods, are also linked in the comment section. If you are interested, go check them out.